So we are here with the next question. This time we have first missing positive. Okay, let's try to read the problem statement. The problem statement is saying you are given an integer array ARR. Your task is to find the smallest positive number missing from the array. Okay, there is one note given. The note says positive numbers start from 1. We all know that. And the array can have negative integers too. 1 point to notice. Now, let's try to see the sample test cases so that we can have a clear understanding. Here we have the array having numbers 2, -3, 4, 1, 1, and 7. So the natural number, the set of natural numbers that we have is beginning from 1, correct? Like this, we have 1, 2, 3, 4, and so on. That is what we need to check, that if the numbers are present in this array or not. The moment we find a natural number that is not present in my array, that is going to be my answer. Let's first look up for 1. So here if we see, okay, I found 1. That means this possibly cannot be our answer. Going on to 2, I got 2 being present in the array. I checked 3. Well, 3 is not present in the array. This is -3, but we cannot consider that. So -3 is present in the is not present in the array and is my smallest positive missing number. Thus, the answer is returned. Going on, checking the next example. The next example has 5, 3, 2, 5, 1. Again, these numbers, and we have the set of natural numbers 1, 2, 3, 4, and so on. We need to check 1. 1 is present. 2 is also present. 3 is also present. But when we go on looking for 4, we find out that 4 is missing from this array. Thus, we return 4. Now, there's one situation with this example. Let's write down the values. Here, all the values are negative. Just this one, which is 0. Now, for this case, the very first value that we are going to check for, 1, we would not find that. We cannot find that. See, 1 is not here. This 1 is going to be the answer for this case. Now, I hope you have understood the question clearly. Now that you have an idea about the question, we need to figure out that what actually we need to focus on and what values we actually need to avoid our focus from. So let's try to see. Let's suppose, again, let's take the example of this array only. I took 2, -3, 4, 1, 1, and 7. Then what is the size of this array? 6, right? N is equals to 6. Now, if we are looking for natural numbers, which values are we going to ignore? Which values are completely unnecessary for us? First of all the negative ones, all the negative values that we have are completely unnecessary values for us. Along with that, 0, we do not we are not considering that. We are just taking care of our natural numbers. So if we talk about an array having all of these numbers, only the natural ones, not the unnecessary ones, then what could be the maximum possible range of our answer? Well, then it could be 1, 2, 3, 4, 5, 6. If we are having if we have to make an array of 6 elements, then this could be the possibility. This could be the only possibility. That is the thing. Any value that we have bigger than 6 cannot be my answer in this particular situation. Any value which is smaller than 0 or 0 cannot be my answer. The only range for this question I'm going to be getting my answer from is going to be this 1 to 6. Now, we know that what values we need to look our answer from. I hope that's clear. One more thing, out of these all cases, suppose you have this array mentioning 1, 2, 3. Now, what is going to be the answer for that? Which is the first missing positive number? Well, in that case, we know that 1, 2, and 3, all of the values are present, right? What is the next value? If the array was one step longer, what would have been? It would be 4. Thus, in this case, you would be returning 4. So now I hope you have understood the question clearly. You have gotten account of what are the necessary values, what are the unnecessary values, from what values you are going to get your answer. Now that you are clear with that, let's move ahead and start forming the approaches. Talking about the approach 1, when we have this array and we do care about the sequence because it is going to make our work easier, the very first thing comes to our mind is let's sort this array, right? So that we can make the comparison easily. Because, okay, let's go ahead and sort these one. We have -3, then we have 1 on this one, then we have 2, 4, and 7. Okay, all of the values are sorted. Now comparing the values is going to be very easy for us. Now that we do, what value should we compare with? Well, of course, our natural numbers. The first natural number is going to be 1. So and it is going to be a possible result. So what I will do is I'll make one variable result res, and I will initialize it with the value 1. Okay, because if 1 is not the answer, then we are going to keep on increasing it till we find the answer. Okay, let's see. I start my traversal from this point, from this first element. My I pointer is here. I see, okay, -3 is kept. Now, this comes under the category of unnecessary values. We are not taking care of that. Okay, that means we can simply go ahead. Now, once I go here, now this value is going to be considered, and I need to compare it with my result. I need to check that whether this is equal to my result or not. Well, yes, it is equal to my result. You can see. And that this happens, you know that the current result you were assuming so far, in our case 1, is present in the array already. That means it is not going to be an answer. Thus, we would increase it by 1. Now, moving ahead, I am encountering 1 again, but this time you see the result is already more than that. In that case, you just need to keep on moving. Now, again, you go at that point, at this point, you encounter 2. Once you encounter 2, you know, okay, result is equals to that. That means 2 cannot be a possible answer as well. Then you are going to increase it by 1. You move one step more and you find 4, and you find 4, and the result you have is 3. You realize what is happening here. The value in the array are in sorted format, and you cannot get this 3 anywhere afterwards. Okay, so at this point, when your ARRI, your ith value becomes bigger than the result, you know that you have already got your result. So you can simply break out of the loop and you can return this result. And what is going to be the complexity of this one? Well, because we are sorting the elements and considering that we are using the inbuilt sorting methods, then it's going to be costing you n log n, plus we are traversing this array that would be order of n. Eventually, we just need to care about this one. So the complexity, the time complexity for this approach is going to be order of n log n. Now, what is going to be the space complexity of this one? Well, for space, we know that we are not taking any extra space. We are just sorting this array up and we are taking up one variable result. That's all. Nothing auxiliary which is growing with our input. So my space complexity is going to be order of 1. Now that we have already analyzed the complexity, let's try to quickly look up the code for this as well. So here we have the code for the same. We are sorting up the array. We are taking one variable result. Initially, we are putting the value 1. Then we are traversing in our array. Every value that I get, I just need to compare that whether that is equal to a result or not. If that is equal to result, I'm going to increase the result by 1. And if there is any other case, we would completely ignore the value. Okay, if it is negative, if it is 0, we are going to keep on ignoring the values. The moment we find if this is not the case, then if my num becomes greater than the result, num is the ith element. If my ith element is bigger than the result, that means we need to break our loop from there and we need to return the result because we have already found it. Okay, quite simple implementation, but not that optimal. We are taking order of n log n amount of time for this. So let's move on to our better approach. Following up with our approach 2, well, in this, we will use some extra memory so that we can just try to reduce the hassle around the sorting of elements that was taking n log n, like n log n time complexity. So for that, in this approach, what we do is we take up the array that we have. Now what I will do is, I know that the value n is 6. What is going to be the possible range? 1, 2, 3, 4, 5, and 6, right? I would make a corresponding array of this, of these many elements. Now that I know, this array is actually would be a Boolean array, initializing every value as false. This signifies that whether we have found the value or not. Now these index are actually going to signify and going to relate that what value should be kept here. 0, that means when your I is 0, that means this is the correct place for 1. Okay, we can find it just by adding 1 to it. I plus 1, 0 plus 1, 1. This is the correct place for keeping 1. This is the correct place for keeping 2, so on and so forth, like this. Okay, so this is how I'm going to be tracking whether I have found an element or not. Let's try to iterate our array from this point till this point. When we do so, we find 2. So at the place of 2, which is the correct position for 2? The correct position for 2 is 2 minus 1, resulting in 1. Okay, I go to my Boolean array, or you can say the result or answer array. In that, I go and I convert this true to false. I convert this false to true. Going ahead, I find a value which is not necessary, right? So I completely just ignore that value. I go to 1. Now what? I go to 1. I need to find out its correct position. 1 minus 1, it's 0. For this, I changed it to true, that I found it. I went to 1. I again did the same thing. It was already true, so need not to change. or if you just change it, you will just be overwriting it. Then you go to 4. Okay, the correct position for it for this one is 3. So for it at the third index, I've put true. Now going ahead to 5, I know the correct position for this one is this 5 minus 1, 4, the fourth index. So it is also converted to true. Once that is done, I can see the array has true, true, false, true, true, and false. Okay, these are the values. Now, once my array is built up, the Boolean array is built up, it would look something like this. Now, out of this array, I just need to traverse it once, and the first value that I get, which is going to be false, is actually the result that I want. It is the correct position for the result that I want. That means, okay, true, true, false. The index for this is 2. What answer do I need to give? This plus 1, because this is just the position, right? You need to return the answer 3, and 3 would be a final answer. And yes, we know that it is correct. We have already seen the case. Now, how much complexity are we taking in this one? Talking about the time complexity, we are just taking one iteration and we are not doing any extra thing. We are not performing sorting here. So that means my time complexity becomes order of n. But what is the trade-off of this optimization? That we are using this extra Boolean array, which is going to be as long as my input. Thus, having a linear relation with the input, space complexity also is order of n. Now, the thing is this optimal enough? Can't we think of any better approach? We can, but let's quickly see the code for this approach and we would move ahead to the best approach then. So here we have it. I have kept this variable n to keep the track of the length of my array. Then I have made this array visited. Okay, this Boolean array, and I've named it visited. Okay, it is having false as many times the length. Now I'm iterating through my array, and every time I'm seeing if my value is in the range of 0 less than equal to n, that means one of the valid values. Okay, if that is so, then at its correct position I'm going to mark true. That means ARRI, the ith value, minus 1. That is what we were doing in our example. So here we would mark true. Once that is done, once this loop has executed successfully, we would have marked all the values as true which appeared in our array. Then I need to go through my this visited array, and the first false value that I get, I just need to return true. I just need to return that value from there. So here in this case, I'm running a loop from 1 to n plus 1. So I've here just like taking care of that plus 1 thing that I would have done if the loop was going from 0 to n. So now I will check all the values that my visited array has, and every time I check it, the moment I encounter a false value, I return that index. That means I return the correct value. This approach is taking the space complexity of order of n, which is not acceptable. We need to improve our thinking process a little more. So for that, let's go to our next approach. Well, coming on to this approach, this approach will require you to have a knowledge about cycle sort. Okay, well, cycle sort is a very amazing algorithm, but it has a few restrictions, such that where can you use cycle sort? Well, only if you are talking about numbers from 1 to n. If you're talking if you're talking in terms of numbers 1 to n for your n length array, only then you can use cycle sort. Let me give you a single small example of cycle sort, and you will understand it clearly. Okay, assuming this is my array, the size is 6 and the values in it are from 1 till 6. Now once I have this array, I need to sort it. We can go for the generic ones, but that would take n log n time. Let's see how much time does cycle sort take. Okay, you try to analyze it with me while I solve it. Name of this array is ARR. Now once I start iterating, you know the indices already. Now once I go to this first index, I see, okay, 3 is kept here. Well, if we already know that the values that we have to arrange are from 1 to 6 in this case, then what is the correct value that should be placed here? What is the supposed correct value that should be here? Actually, it's not 3, right? So where should 3 lie? What is the correct position for 3? Well, if we are going by the index, if we do 3 minus 1, we get 2. 2 is the correct position that I'm talking about the index. The second index is the correct position for us to keep 3. That is what we will do here. Okay, we will swap these two values. 2 will come here and 3 will go there. Now that we have 2 here, is 2 the right thing to be here? Well, still not, right? 2 is not the correct position. 2 should be somewhere else. Where should 2 be? 2 be at 2 minus 1, 1. That means the first index. So we will swap these two values. So once I swap these two values, it will be 1 here and 2 here. Now again, we compare that is this the right position for this value? Well, this time, yes, it is. Because if you do 1 minus 1, you get 0 and you're already here. That means this is the right position. Once you get that, you move ahead. Now you again check that. Check this element, whether this element is kept at its right position or not. Yes, this is also kept at its right position. You compare this one, then you try to compare this one, then you try to compare this one, and then you try to compare this one. Luckily for us, all of the values are now sorted. You saw what we did? Because we were having an idea what our answer is going to be like, we related that with the indices. And we just like asked one single question at to every element, whether you are kept at the right position or not. If you're kept at the right position, it's fine, we go ahead. If you're not kept at the right position, then for that particular element, what is the right position? We go there and we keep that element and we swap the values. Simple, correct? Simply, if I have to put up a chart here, you have your ith value. You just need to check if it is at the right position, do nothing. If it is at the wrong position, then you keep it at its right position by swapping the value which is kept at that position. Okay. Now I hope this has completely made sense to you and you understand the cycle sort. The thing is, how much work did we do? What is the time complexity for this one? Well, if you closely observe, we only made swaps within this range. Okay, that is also a limited number. And we just moved through this array. We are not moving beyond this, correct? Or we are not even reiterating it. We're just iterating it for the one time. So that means time complexity for this sorting algorithm is going to be order of n. Now that you have understood this sorting algorithm, how are we going to utilize that in our question? Let's see it with one example. Assume I have this complete solution. I have this complete array here. I just need to perform the cycle sort with a few little diversions. Okay. I went to my first element. I checked whether this is the correct position for keeping it or not. Well, here I find out, okay, 2 should be kept at 2 minus 1, 1. So yeah, it is not at its right position. I would make it go at its right position by swapping it with the element that is kept there. I'll swap these two values. So once I swap these two values, I'll get this. Okay, 3 is now here. Now, is 3 at its right position? Well, we actually need not to check it because these are one of the values that we need to avoid. This is negative. If we fall into that case, we go ahead. We move ahead. Now I'm at 1. Is 2 kept at its right place? Well, yes, it is kept at its right place. Then again, I move ahead. I go at this position. What is going to be the correct value for this position? 2 plus 1. That means 3. It is not 3. 4 is not at its right position. We need to shift 4 towards its right position. 2 should be kept at 3. And now here we have 1. We would swap. So once I swap, I have this. This value becomes 1. This value becomes 4. Again, I'm still at 2 and I'm looking for this value. Is it the right one at its place? It is not. Then we are again going to swap. And once we again swap it with its correct position, we would actually shift -3 here and 1 would go here. Now, again, now that we have -3, we know if we have a number which is unnecessary, we do not take care of that. We move ahead. We moved ahead, and I can see 4 is kept here at its right position. Fine. I moved here. Well, we actually have a smaller value now. Okay, we need not to care because I have come to this like till this place, and the value that I'm storing is less than that. No need to care about that. Moving ahead here, is this value kept at its right position? It is one of the bigger values out of the range that we are looking for. That we have completed our traversal from this point till this point. My array now looks like this: 1, 2, -3, 4, 1, and 7. Now I just need to begin my traversal from this point and I need to check whether all the elements are kept at their right position or not. The moment I find that, okay, something is wrong, that means either like I do not find the right element at its position, that means that element is missing. 1 is at its right position, fine. 2 is at its right position, good. I do not find 3 here. That means 3 is missing. I'll return 3 as the answer. As simple as that, right? So this is how my algorithm is working. My this algorithm that we have formed using cycle sort is working. Okay. How complex is this algorithm? How much time are we taking here? We are just taking order of n amount of time. Okay, we are just performing some swaps and that is within the limit. That's all. Now, are we taking up any extra space to store any element, any space which is growing with our input? We are not taking it. So the space complexity is order of 1. Now that we have seen that this is a pretty optimal solution, we know that this can work for us. Okay, let's see the code for this. So here, what am I doing? I'm taking up this variable n to keep the track of the length of my array. Then I'm moving in my array. Every time I'm checking that while I have the number in my range and it is not in its correct position, I have the number in my range. That means I'm avoiding the negatives. I'm avoiding 0 and any bigger value than n. I'm avoiding all of these three conditions. If the value that I have is in the range and it is not at its correct position, then what will I do? I will put that at its correct position simply by swapping. And once that is done, like once this loop is completely executed, I just need to go through my array again. Okay, I'll just go through my array again. I'll check whether the elements that are kept are at the right position or not. If they are not at the right position, that means I is not equal to arr I minus 1, then we will simply return that I. That means, okay, at this index, okay, not the correct value, the correct value is not present. That is what we have to return here. Okay, once this is not the case, okay, my complete array is formed. Assume my array was a 4 length and all of these values are present. And eventually, if no I is returned, because we would have all of these values present at its right position, and for that case, we need to return n plus 1. That means fifth value is missing. We have already seen this case before, right? So this is a pretty optimal solution to this question. Let's try to run this code now. So here's the code for that. Let's try to compile and run it. All right. On compiling, it is giving us the expected output. Let's try to submit that and test it against all of the test cases. Well, yes, it has passed all of the test cases, and we have successfully made our optimal solution. So if you have liked the approach, if you have liked the cycle sort algorithm that we have taught, do mention that and share it with your friends. Thanks.